Welcome to our first video in our Class 18 series of lecture videos. Uh, in our last video of our Class 17 series, we talked about reducing agents for carbonyl compounds. One of the reducing agents was sodium borohydride and methanol. And we even talked a little bit about potential stereochemical consequences of reducing a carbonyl. So, we'll further explore some stereochemistry in these reductions. I'd like to remind students that diastereomers must come from diastereomeric transition states that may be different in relative energies. So if you have a reaction that produces diastereomers, you might favor one over another because the transition state leading to one might be much lower than leading to another. So here we've got a pure enantiomer. We have this compound that has only 1 and 1 stereocenter, which is an absolute configuration of R, and we're subjecting it to reduction with sodium borohydride and methanol. We might get the SR stereoisomer, or we may get the RR stereoisomer, and the way that those two are related to each other are as diastereomers. If we were to take a racemic mixture of that particular carbonyl compound, so equal amounts of R and S, we would get 1 and then the enantiomer of 1, and we would get compound 2 and then the enantiomer of 2. And of course, while 1 and the enantiomer of 1 would be in equivalent amounts, as well as 2 and the enantiomer of 2, the net amount of 1 and its enantiomer might be different than the net amount of 2 and its enantiomer. So, like I said, we could think about a diastereoselective reduction. In this case, we know the major and minor products. Why might this be the major product? So which side of this carbonyl face, as it's drawn, did the borohydride approach to deliver the hydride to the carbonyl? And so if the hydroxyl group is pointing up, that borohydride must have come from the back face, which is reasonable because we have this isopropyl group that is helping to shield the top face of that carbonyl compound. So that's why we end up with this as a major product. And the stereoisomer, the diastereomer in fact, where the hydroxyl group and the isopropyl group are trans, as the minor isomer. So this relies on a difference in diastereotopic transition state energies. So the lower activation energy pathway always goes faster. That said, one could think about an enantioselective reduction. So, we could think about reducing this carbonyl compound to only favor one enantiomer over another. If we did not use any sort of chiral catalyst, we would expect a 1-to-1 mixture of enantiomers. However, there are chiral catalysts and schemes available where we could actually favor one enantiomer over another, but you have to employ a chiral catalyst, so some sort of catalyst that differentiates one transition state over the other, because the transition state will look diastereotopic. So our next topic is quite interesting because it kind of gets at the holy grail of organic chemistry, and that's carbon-carbon bond formation. So if we can add a hydride to a carbon of a carbonyl group, could we not form carbon-carbon bonds with carbanions? And of course the answer is yes. And so let's look at this. Say we have this carbonyl compound with R and R prime groups on it. Instead of a hydride, here we have a methyl carbanion, and we're taking its 2 electrons and using them to form a bond to the carbonyl carbon. If we do that, we break the double bond between the carbonyl carbon and oxygen, and we push a pair of electrons up on top. oxygen. Now, oxygen has a formal minus charge. In a separate second step, we add acid to neutralize our alkoxide, which is, a fairly strong base. It's not as strongly basic as our methyl carbanion, so we'll be able to compare these things soon. And what do we get out of this? We get an alcohol. So how do we make a methyl carbanion? Well, methane isn't very easy to deprotonate. The pK of methane is about 50. However, you can reduce a haloalkane. So here we have methyl bromide. Maybe we have something that's a good reducing agent. So gain of electrons is reduction. So a reducing agent would want to give up electrons. So let's say somehow we popped an electron in our carbon-bromine antibonding molecular orbital. It would feel uncomfortable. It might even help break that bond to give us a bromide anion and a methyl radical. And let's say we pop an electron into that singly occupied p orbital on that methyl radical, we get our methyl carbanion. What kind of reagents are sources of electrons? Well, things like lithium metal, for example. I have a nice bottle of this stuff in lab. If we added that to methyl bromide, we would generate methyl lithium. Of course, we need a couple of equivalents because we need a couple of electrons. And so the other thing we're forming is lithium bromide. Sometimes you will see these carbanions written with polar covalent bonds between the carbon and the metal. Sometimes you will see them written in an ionic sense, like a methyl carbanion with a formal negative charge on carbon and a lithium with a formal positive charge. We call these things, well, this in particular, alkyl lithium reagents. We have another name for these organometallics, Grignards. And so those are typically ones that you see with magnesium. So let's look at that. They function very similarly. So here we have our methyl bromide. We throw in magnesium turning, so we have a source of magnesium. Now magnesium's on a place in the periodic table where it can give up 2 electrons to reach a closed shell, so we only need 1 equivalent of magnesium. And we'll go ahead and insert ourselves between the carbon and bromine bond. We can write this as methyl magnesium bromide, or we have a deeper understanding that we really have a methyl carbanion, a magnesium 2+ cation, and a bromide anion floating around in our solution. So methyl lithium and methyl magnesium bromide are examples of Grignard reagents, although my British colleagues like to refer to the lithium versions as alkyl lithiums. They are organometallic reagents because they contain an organic part and a metallic part. Grignards are very basic, so they are never made in the presence of protic solvents. They're usually made in ether, and organic chemists have to take great care to make sure that their ether solvents are free of water, so anhydrous. You can use brominated hydrocarbons. You can even use chlorinated hydrocarbons or iodinated hydrocarbons. We would not see fluorinated hydrocarbons in this reaction. So primarily chlorine, bromine, and iodine. So here we've got 1 chloropropane. We're making propyl magnesium chloride Grignard. And of course, we generate a lot of heat when we do this reaction. Most reactions are enthalpically driven. If you were to do a Grignard reaction in lab, typically you would see your ether boiling as this gets underway. Here we have 2-bromo-2-methylpropane, or tert-butyl bromide. We throw in magnesium. Now we're using a different ether solvent, THF. It's got a little higher boiling point, a little less likely to catch on fire as ether under an oxygen atmosphere. Anyways, here we've got tert-butyl magnesium bromide. And some of these Grignards can be kind of dangerous, especially these ones that where the carbanions are sort of sterically hindered, they can even be pyrophoric, so to a point where they would catch on fire in air. And so we used to have undergraduate students make Grignards. We no longer do those sorts of labs in our microscale laboratory experiments, although we may bring them back yet. Anyways, we'll start the next lecture video with a little bit more of a discussion of what's going on as we make these Grignards.